Okay, so this week we're going to talk about something called the traveling salesman problem. This is actually what's known as an open problem in mathematics. It is a problem that needs to be solved and has some algorithms that we're going to use to try and solve it. But the truth is, a really good, efficient method of solving these problems has not yet been developed. We're going to see what methods have been developed, but we'll find that only one of them will lead us to always having the best solution, but that one is so cumbersome and so terribly hard to do that it's really not a good algorithm for this. All right, so here's the idea of a traveling salesman problem. Years ago, we used to have traveling salesmen going door to door and visiting people. And the idea, of course, is they have to visit certain cities and visit certain neighborhoods. And we want to minimize the cost that it takes for them to travel from place to place. Now, what we might think of now in terms of the use of this rather than traveling salesmen, since we don't tend to get many salesmen at our doors anymore, we might instead think of truckers needing to have the shortest amount of money or spent driving from place to place, or the shortest distance from place to place. We also might think of people who have to go to different cities in order to conduct their business, and what's going to be the lowest airfare, what's going to be the cheapest way for them to do that. So there's a lot of different applications if we start thinking of them, of the traveling salesman problem. Now, the first problem, the first algorithm we're going to look at, the first way to solve these problems, is called brute force. And we'll see that brute force will lead us to the solution, but brute force is incredibly difficult to do. So let's look at an example. Okay, so for the brute force algorithm, it's an exhaustive search. We're going to find every single possibility that could possibly be a Hamiltonian circuit, and we're going to choose the smallest one. So we're going to list all the possible Hamiltonian circuits. Recall, those are the ones that visit every vertex. They don't have to visit every edge, just every vertex. We want to find the length of each circuit we find by adding the edge of the weights, and then select the circuit that has the smallest total weight. So for the brute force, we have to find every single Hamiltonian circuit. And that's easy enough if we've only got 4 vertices, as we do in this picture. But imagine if we have 20 or 25 vertices and we're trying to find every single Hamiltonian circuit. So let's take a look at finding all the Hamiltonian circuits here. We'll just pretend that A is our starting point. It doesn't really matter. It's a circuit, so we're always going to return back again. So it doesn't really matter what our starting point is to begin with. But let's list everything that starts with A. Now, in order to do this, let me do the draw feature. Everything is connected. So notice that A is connected to every single vertice, B is connected to every single vertice, C is connected to every single vertice, and D is. Our graph is what we call a complete graph because every vertex is connected to every other vertex. All right, so with that in mind, let's list all possibilities like so. I'm going to start with A, and let's just list them in alphabetical order. A, B, C, D. All right, that's one possible circuit. So if we think of A to B to C to D and back to A, let's get the weights there. That's 4. To C will be 13. Then to D will be 8. And then back to A will be 1. All right, so let's see, that's 17, 25, 26 for our weight. All right, now let's just mix these letters up and then we'll look at the graph. Let's keep A and B in the same order, but let's go to D and then C and then back to A. So notice I'm just sort of flipping around 1 or 2 letters, still with A as my beginning point. All right, so A to B is 4. And then if we go to D, that's 9. And then if we go to C, that's 8. And then back to A will be 2. And let's see. That's going to be 13, and 8 will be, and that is an 8. 13 and 8 is 21, and that's going to be 23. Well, that one is shorter thus far. Okay, so I think I've done everything with A and B first, so let's go to putting A and C first. I'll go A, C, B, D, and back to A. All right, so A to C will be 2. C to B will be 13. Then we're going to D, which will be 9. And then we're going back to A, which will be 1. All right, so let's see, that's 15, 24, 25. All right, now let's keep A and C just like that, and I'm just going to flip my D and B right here. All right, so A to C. A to C will be 2. C to D. C to D will be 8. D to B will be 9. And then back to A will be 4. All right, so that's 10, 19, 23 again. All right, so, and let's notice something. When I listed this ACDBA, this is really the same circuit as this one up here because it's just backwards. ABDCA, ABDCA. So really, I've gotten the same circuit there. All right, so that was everything. So since I've duplicated with this one right here, the one that was up here, let's notice that next we would choose, if we kind of did the same process I've been doing all along, to put AD first, and then we'd go BCA. But AD first, actually AD, BCA is this one in reversed order. And then, so notice, if I do what I've been doing and put AD, and then next would be BCA, well, that's really let's see, A, G, B, C, A. It's just traveling this one in reverse order. So it's the same circuit as this one. And then the next one I would list would be A, D, and I would switch the B, C, A. And let's notice again, that's going to be one of these others as well, backwards. Let's see, it's going to be A, D, C, B, A, right there, backwards. So now we're starting to duplicate this one, and this one is a duplication of this one. So really, these three are our only paths. Now, you might say, well, what about if we started at B? What if we started at C? Well, really, we're going to get the same circuits. It's just that if we started at B with this circuit right here, we'd have B, C, D, A, and back to B, and it's really the same circuit, just starting at a different value. So we still would get 26. So we only have to do this for one vertex. And let's notice there were 3 different Hamiltonian circuits, and that might not seem too bad to list those 3. However, we'll see in a moment what happens when we get beyond 3. So this is our shortest path right here. And we used this brute force algorithm, and we found the shortest, the minimum cost is $23. All right, so, or 23 miles. It really doesn't tell us what we've got here. All right, so Let's take a look at something else though and determine what if, say, I had, instead of these 4 vertices, what happens if I try to list all of the different Hamiltonian circuits for 5 vertices or 6 vertices or 7 vertices. So just when we get beyond 4 vertices, let's see how many circuits we end up having. All right, so we've got a formula for that. So here's our formula. This may have some symbols in it that you're not really sure of. All right, so half of our duplicates are in reverse order. We kind of saw that as we doing our example. So here's our formula. You might want to put that down on a little cheat sheet for later. The number of possible circuits in a complete graph is n minus 1 factorial over 2. Now let's talk about what factorial means. Let me just do one over here. Let's say I've got 5 factorial. Well, 5 factorial, what that means is 5 times 4 times 3 times 2 times 1. Okay, so we start with this number and we multiply every single number going down until we get to 1. And so this is, let's see, 20, 60, 120. So if we had, for example, 8 factorial, that would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And depending on your calculator, there is a button or a 4 factorial, but it may be difficult to find depending on what kind of calculator. So it's just easiest to go ahead and stick this thing in as 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And that's 40,320. So if you were visiting just 8 cities, we can see that this is going to turn into a huge number of circuits. Now, this isn't our formula. This is just discussing factorial. So let's go back to this idea of, let's say that we had 8 cities, and let's put it in this formula. According to the formula, 8 minus 1 factorial over 2 is going to be the number of circuits we would have. All right, that's really 7 factorial over 2. Well, let's find 7 factorial. That's 7 times 6 times 5 times 4 times 3 times 2 times 1 over 2. Well, let's multiply out that top. 7 times 6 times 5 times 4 times 3 times 2 times 1 is 5,040. Let's divide that by the 2 on the bottom. And we get 2520. So if we used the brute force algorithm on a problem where there were 8 different cities to visit, just 8 cities, we would have to make 2,520 Hamiltonian circuits. You can imagine how time-consuming and how terribly long and hard this would be. All right, so we see that the brute force algorithm is just not a very good algorithm to do this with.